Good morning, dear participants of the conference. In this slide you can see the title of my presentation and our team that worked on this study. In vacuum arc deposition, a jet of cathode vapor plasma is formed by the vigorous evaporation of the cathode material. In addition, the arc discharge also produce small liquid droplets, commonly referred to as macroparticles or microdroplets. The evaporated cathode material is deposited on any substrate, intercepting part of the jet, fuse forming metallic or semiconductor coatings, depending on the cathode material. The coated cutting tools has a great wear resistance, lower coefficient of friction, and greater heat resistance. All these factors make it possible to increase the operation time of cutting tools by 2-3 times. Macro droplets degrade coatings as follows: heterogeneity of structure, high porosity, and surface roughness. The purpose of this study is research the effect of additional gas plasma on reducing the number and size of microdroplets following on the substrate, and influence of pulse periodic low pressure arc discharge mode. This slide lists the ways to reduce microdroplets in coatings. In our research, we use first, third, and fourth methods. The coatings were deposited using a vacuum arc plasma-assisted method on a quadra installation with chamber volume of 0.2 cubic meter and a planetary rotation mechanism for the substrate. To generate gas plasma necessary for purification, heating, and additional activation of gas component of the plasma, a plasma source with a thermionic cathode and halo cathode, named pink, developed at Institute of High Current Electronics, was used. The installation has a high vacuum pumping system based on turbomolecular pump and a system of injecting two gases, argon and nitrogen. The samples were used to steel chromium 20 molybdenum vanadium, pre-polished and cleaned it from contamination with acetone. Two installation schemes presented on these slides were used. The left figure shows the traditional scheme of coating deposition by a plasma-assisted method. The picture is represented by a top view. The right figure is deposited experiment scheme with increased plasma concentration, represented by a front view. The sample with a diameter of 20 mm was placed on a satellite of the table. The sample was initially purified and heated in argon plasma to a temperature of about 3050 degrees. When the coating of titanium nitride with a thickness about 2 microns was deposited, during the coated deposition, a negative displacement potential of 175 volts was applied to it. Some problems? Okay. This slide shows an oscillogram of a current of a pulse periodic arc discharge with a cathode spot. During the deposition of titanium nitride coating, minimum current was 55 amperes. Maximum current was 95 amperes. The effective value of the current was 68 amperes and the pulse duration was 4.25 milliseconds. When depositing in stationary mode, the effective current value of the titanium cathode was 70 amperes. The influence of several factors of the size of microdroplets in the titanium nitride coating was tested in the work. This research used titanium cathodes with a diameter of 80 and 100 millimeters. In addition to the traditional depositing mode, a pulse mode, and a mode with an increased concentration of gas plasma and combination of two methods listed above we used. The total of 8 experiments were carried out presented in the table. This slide shows image of the surface of specimens under a microscope. To study the droplets was carried out on a sample with area of 22,500 millimeters square. To increase the accuracy of calculation, 5 regions were allocated for each sample when the results were averaged. The results of the investigate indicates a significant effect of the increased plasma concentration on the size and number of microdroplets. The distance what microdroplet passes from cathode surface to substrate is about 55 centimeters. When interacting with electrons due to a greater mobility of electrons, microdroplet should equate a negative potential. This means what microdroplets must experience intense interaction with charging particles when moving towards the substrate. This is several dozen Coulomb interaction, even if among these collision there will be only a part collisions with ions, will at least contribute a changing the trajectory and trajectory of microdroplets, and it will not reach the substrate. As a result of conducted investigation, the following results were obtained. We use a pulse periodic mode of arc discharge with a cathode spot leads to a decrease in the number of microdrops by 50% compared to the stationary arc mode with the same effective value of the discharge current. Second, the generation of gas plasma is the substrate region at the discharge currents comparable to the current of an arc discharge with a cathode spot allows reducing the number of microdrops of the substrate by 35% compared to the stationary arc mode at the same effective value of the discharge current. Third, the simulation use of these two approaches reduce the number of microdrops on the substrate by about 67%. Fourth, the estimates show what the probable reason for the decrease in microdrops on the substrate when using a high-density plasma is the influence of the interaction process with electrons and ions in the gas-metal plasma is a deviation of the microdrops from the initial trajectory of motion due to a large number of Coulomb interaction in a high-density plasma. Thank you for your attention. I will be happy to answer your questions.